Welcome to the Deep Dive. Today, we're going on a trip into the world of quantum computation and logic. I'm really excited to explore this with you. Our source material today is excerpts from Quantum Computation and Logic, a book that delves into some, well, pretty mind-bending concepts.
Yeah, it's a fantastic choice for a deep dive.
Oh, yeah.
This book really sets the foundation for understanding how quantum mechanics changes, like our whole understanding of information and logic.
Okay, so let's start unpacking this. So the book begins by comparing classical and quantum approaches to information, right? It talks about how in classical physics, a pure state is thought to contain complete information. Like, they use the example of the state of a gas molecule.
Right, or even something bigger, like the moon.
Yeah, like the moon. The book says an all-knowing being would theoretically have a complete understanding of every single aspect of the moon. Even if we humans don't.
It's like that idea from Leibniz,
Yeah.
a complete concept. Basically that everything knowable about something is like already contained within its concept.
Yeah, that makes sense. So it's all about certainty in classical physics. But then, well, this is where things get really interesting. Quantum mechanics throws in this wild card, inherent uncertainty, even for like an all-knowing being. The book uses the example of an electron.
Right, and what's so fascinating is that you can't know both the velocity and the position of an electron at the same time. Like with complete certainty, this is the uncertainty principle, and it's a huge difference from how we think in classical physics.
So it's like the universe is playing hide and seek with information at the quantum level.
Wow. And then this uncertainty, well, it changes everything when it comes to logic. The book explains how quantum events they kind of defy traditional logic. Boolean logic, which is all based on classical physics and certainty.
Exactly. I mean, Boolean logic is all about true or false, and that just doesn't cut it in the quantum world.
So then how is quantum logic different from that classical logic? Well, the book says that instead of true or false, quantum logic is, it's three-valued. And it's tied to the fact that quantum mechanics is all about probability. For example, let's say you have a quantum system in a specific state.
Okay.
The book uses the example of an event, represented by a closed subspace within that system.
So like an event could be an electron changing its energy level or, I don't know, a particle decaying.
Exactly. And the probability of that system verifying that event, it's calculated using the Born rule. And that rule involves the squared length of the event's component. It's a lot more complex than just, the simple either of classical logic.
So it's not just whether something happens or doesn't happen. It's like a whole spectrum of probabilities. It's a lot more complex, but also a lot more interesting, especially for someone who wants to understand how we even know things in the quantum realm.
For sure. And the book really goes into how this three-valued logic and the uncertainty changes how we think about truth. Like, it challenges what it means to know something in the quantum world.
Okay, so let's move on to another big idea from the book. Quantum entanglement. It really emphasizes how important entanglement is for quantum computation and how it leads to that famous EPR paradox.
Right, the EPR paradox, named after, well, Einstein, Podolsky, and Rosen. It's a thought experiment that challenges some of the foundations of quantum mechanics.
I've always been fascinated by this paradox, but I'll be honest, it's really confusing. Can you maybe break it down for us?
Sure. It's all about a thought experiment with two entangled particles and their spin. So imagine you have these two particles, and they're linked in a special way. Like, you measure the spin of one particle, you instantly know the spin of the other one, no matter how far apart they are.
Oh, okay, I get that. It's like they're two dancers, mirroring each other perfectly, even if they're miles away.
Yeah, great analogy. The problem is, this instantaneous connection seems to violate Einstein's theory of relativity.
Yeah.
The one that says nothing can go faster than light.
I see. So how does quantum mechanics resolve this?
Well, that's the paradox. It really challenges how we think about locality, and it makes us question whether quantum mechanics is even a complete description of reality.
So are we saying information is traveling faster than light between those entangled particles?
Well, that's one interpretation, but it causes more problems than it solves. The book actually makes an interesting comparison between this paradox and Gödel's incompleteness theorems.
Wait, Gödel's incompleteness theorems? Hold on. Those are about the limits of formal systems in math, right? What do those have to do with entangled particles?
It's a really interesting connection. The book suggests that just like Gödel showed, there are true statements that can't be proven within a formal system There might be things about reality that quantum mechanics just can't fully explain.
That's mind-blowing. So maybe the EPR paradox is pointing to something deeper that we haven't grasped yet?
Yeah, it's definitely a possibility that physicists and philosophers are still exploring. And this leads us to another fascinating concept that the book touches upon: teleportation.
Teleportation. Now we're getting into sci-fi territory. But wait, the book suggests that teleportation might actually be possible based on entanglement.
It's true. It's one of the most amazing potential uses of entanglement. The book even quotes a physicist from, way back in 1985 at a conference, and he was expressing doubts about ever achieving a complete theory of quantum mechanics, hinting that future theories might describe reality in ways we can't even imagine yet.
So physicists were already thinking about the crazy implications of quantum mechanics back then.
Oh, absolutely. And the book goes on to explain how teleportation might be possible, through entanglement.
Okay, you've got to explain this. How does this quantum teleportation magic work?
All right, picture this. 3 entangled particles.
Yeah.
And then we've got 2 observers, we'll call them Alice and Bob. Alice has one of the entangled particles, and Bob has the other 2. Now, Alice wants to send some information to Bob, quantum information.
Okay, like what kind of information are we talking about?
It could be the state of a qubit, which is kind of the quantum version of a bit in classical computing. But here's the thing. Alice doesn't actually need to know the value of the qubit to send it to Bob.
Wait, hold on. How can you send something if you don't even know what it is? It's like sending a letter without knowing what's written inside?
Exactly. That's the beauty of entanglement. The particles are connected in such a way that Alice can measure her particle and instantly change the state of Bob's particles. It doesn't matter how far apart they are.
So it's like the information is encoded in the connection between them, not the particles themselves.
Right. The book describes how Alice does a specific measurement on her particle, and that causes a collapse of the states across all 3 particles. This collapse, plus some communication between Alice and Bob, it lets Bob reconstruct the original information on his end.
So the information isn't literally beamed over, like in Star Trek.
Not exactly, no. It's more like it's transferred through the connection.
Okay, so it's still mind-blowing, but a bit less magical than beaming someone across space. But it still raises a question, right? How can you transfer information if you don't even know what the values are? I mean, it's like sending a package without knowing what's inside.
Well, that's the beauty and the mystery of entanglement. They share a connection that we can't describe with classical physics. When you measure one particle, you instantly learn about the other one, no matter how far apart they are. And that connection lets you transfer information without actually moving the particle itself.
That's pretty wild. It's a good reminder that the quantum world has its own set of rules. Which brings us to the heart of it all: quantum computational logic. The book explains how in this logic, sentences represent pieces of quantum information, and the logical connections are represented by quantum gates.
Yeah, and one of the most interesting things here is that the meaning, the semantics of quantum computational logic is, it's holistic and contextual. It's very different from classical logic, where the meaning of a sentence is built from the meanings of its parts. In quantum computational logic, the meaning depends on the whole system, and it can change based on the context.
So it's like the parts of a quantum system are aware of each other in a way that classical systems aren't.
Exactly. The book goes on to explain how quantum logical circuits are built using those quantum gates. And it gives some examples, like the negation gate, the XOR gate, and the Toffoli gate.
Oh, that Toffoli gate. I find that one particularly interesting because it shows how computation can be reversible in quantum computing. The book even gives an example of how it can make classical logic operations reversible.
You're right. That's a great point. The fact that quantum computation is reversible is a big difference from classical computing, where you often lose information during processing. This has big implications for both the efficiency and the logic of quantum computing.
Okay, so we've talked about qubits. Those are like the building blocks of quantum information. But the book also mentions this idea of qubits. What are those exactly, and how are they different from qubits?
Well, it's like taking the idea of a qubit and expanding it. So a qubit can be in 2 states, right? 0 or 1. But a qubit can be in more than 2 states.
So instead of just like flipping a coin, we're talking about rolling a dice with like multiple sides.
Yeah, that's a good way to think about it. Qubits give you a lot more options for representing and processing information. And that means we have to use higher dimensional Hilbert spaces. Those are the mathematical spaces where we describe these quantum states.
Okay, I'm going to need you to explain that a little more. What do you mean by higher dimensional Hilbert spaces, and Why are they important for understanding quidditch?
Okay, so think of it this way. A quibbit, with its two states, it's like a point on a sphere, right?
Yeah.
But a quiddit with multiple states needs a bigger space to be represented, like a higher dimensional space.
So we're moving from like a 2D representation of a quidditch on a sphere to something more complex, like a 3D object, or even something we can't even picture.
Exactly. And this opens up a whole bunch of new possibilities for quantum computation, like new ways to encode and manipulate information.
This makes me think about something else the book talks about, many-valued logic. It seems like going beyond the binary, true or false makes sense when you're dealing with quidditch, since they can have more than just two states.
Yeah, you're right. The book explores how many-valued logic really fits in with quantum computation. It gives this example of Ukasiewicz quantum computational logic, UQCL, and it has a lot more logical operations than classical logic.
Can you give an example of how UQCL is different from classical logic, like practically speaking?
Sure, so in classical logic, you have conjunction, right? That's the A&D operation. It's only true if both inputs are true. But in EQCL, you can have different types of conjunction, each with its own rules for being true.
So instead of just black and white, now we have shades of gray.
Exactly. It's a more nuanced and flexible way to approach logic. And it makes sense for the quantum world, which is all about probability and uncertainty.
I'm curious, do you think EQCL, with all its extra logical tools, is more powerful than traditional quantum computational logic? Could it lead to better algorithms or even So are you saying that how we interpret language is kind of like a quantum superposition of meanings, where multiple interpretations exist at the same time?
Yeah, that's a good way to put it. The book talks about this idea of vague possible worlds to represent this ambiguity. It's the idea that meaning isn't always clear-cut. It depends on the context and the person's perspective.
Can you give us an example of a vague possible world and how it's related to something like a metaphor?
Sure. Let's say we have the sentence, Alice is kissing Bob. In a classical world, that's pretty straightforward. But in a vague possible world, it could be Alice kissing Bob or Bob kissing Alice. Both possibilities exist at the same time, like a quantum superposition.
So it's like a quantum he said, she said, where the truth is fuzzy and it depends who's doing the interpreting.
Exactly. This is what makes metaphors so interesting, too. Like when you say, my love is a rose, you're not just talking about a flower. You're evoking different ideas. Beauty, passion, even the pain of thorns. All of these interpretations exist together in the metaphor.
I see. I'm starting to see how this quantum way of thinking about semantics can help us understand how we use language and create meaning. It's like we're going beyond the limits of classical logic to a more nuanced and flexible way of understanding things.
And the book even uses an example from set theory, the Skolem paradox, to show how metaphorical thinking can be useful even in math and science.
Wait, the Skolem paradox? That one's all about infinity, right? What does that have to do with metaphors?
It's really cool. The Skolem paradox shows that even in math, which is all about logic and rules, you can have contradictions or interpretations that don't seem to make sense. The book suggests that metaphorical thinking, which is all about ambiguity and multiple perspectives, can help us deal with these paradoxes and gain a deeper understanding.
Wow, so even in math and logic, there's a place for this fuzzy quantum thinking.
It seems so. And the book goes even further. It applies quantum computational semantics to artistic languages, especially music. It analyzes examples from Schubert and Schumann to show how musical themes can act as metaphors, conveying emotions and ideas.
Okay, I need to hear about those musical examples. What kind of metaphorical connections does the book make?
So the book looks at Schubert's song cycle, Die Schöne Müllerin, and it focuses on how he uses music to create a picture of a flowing brook. The repeating musical phrases, often played with a rippling texture on the piano, become a metaphor for the water's movement and energy.
So it's like the music is painting a picture in your mind.
Exactly. Then there's Schumann's Carnival. The book talks about how he uses a musical theme that's associated with his wife, Clara. This theme is often played in a gentle and lyrical style, and it's interpreted as a metaphor for her personality, specifically her connection to consolation and peace.
So the music isn't just describing an object or a scene, it's expressing something deeper, like a person's essence.
That's right. The book also points out connections between Schumann's use of Clara's theme and the consolation theme from Schubert's Ave Maria in Widmung, suggesting a deeper link between these musical ideas.
It's amazing how composers can create these layers of meaning through music. Are there any other examples of this musical metaphor in Schumann's work?
Yeah. The book analyzes Und wüssten's die Blumen from Dichterliebe. Clara's theme appears again, but this time it's connected to the poem's idea of finding solace in nature. The music and words come together to express longing and searching for comfort.
That sounds beautiful and moving. It's amazing how this quantum way of thinking about semantics can help us understand not just science and logic, but also art and human experiences. It makes you realize that these different areas of knowledge are more connected than we usually think. It highlights how interconnected knowledge and experience really are. Speaking of interconnectedness, the book also dives into one of the biggest mysteries in quantum mechanics, the measurement problem. The measurement problem is one of those things that makes you wonder, like, what is reality, really? Can you give us a simple explanation of what this problem is and why it's such a big deal?
Of course, the measurement problem comes from this gap between how quantum mechanics describes systems and what we actually see when we make a measurement. So quantum mechanics says a system can be in multiple states at once, like imagine a coin spinning in the air before it lands. That's a superposition. But then we measure the system. It's like forcing that coin to land. And we only observe one outcome, heads or tails. The measurement problem asks, what happens during that measurement that makes the system collapse from all those possibilities into just one result?
So it's like our observation forces the quantum world to pick an outcome, and that breaks, like, the balance of possibilities.
That's one way to think about it. The book talks about some different explanations for this collapse. For instance, von Neumann thought that maybe consciousness itself is what triggers the collapse.
Whoa, wait, you're saying our minds could be shaping reality at the quantum level? That's wild. Are there any other explanations that don't involve, consciousness?
Yeah, the book mentions some other ideas too, like maybe the measuring device itself is what interacts with the quantum system, leading to the collapse. That takes consciousness out of the equation, but it still brings up questions about, well, what even counts as a measurement? And what's the observer's role in all of this?
It seems like the deeper we go into quantum mechanics, the more questions pop up. It makes you wonder if we'll ever have a clear answer about the measurement problem, or is this something we'll always be trying to figure out?
It's definitely a question that has puzzled physicists and philosophers for a long time. It's one of those fundamental mysteries that lie at the heart of quantum mechanics. But that's part of what makes it so fascinating, right? The search for answers often leads us to even more intriguing questions and deeper insights.
Well, this deep dive has given me a lot to think about. As we wrap up our exploration of quantum computation and logic, what are some of the most important things to remember?
I think the biggest takeaway is just how different the quantum world is from our everyday experiences. And this goes beyond just particles acting strangely. It changes how we think about information, certainty, and even truth itself. We've seen how classical logic, with its clear, true, and false, just doesn't work in the quantum realm. Quantum logic brings in a whole new level of nuance and probability.
And it's not just theoretical. We talked about how these quantum ideas could completely change technology, like imagine quantum computers and teleportation. And the most surprising thing for me was seeing how quantum logic can help us understand language, even art and music.
Exactly. What this deep dive has shown is that seemingly different fields, like physics, logic, and art, are actually connected in some pretty profound ways. It reminds us that knowledge isn't separated into neat boxes. It's all interconnected.
So as we continue exploring this world of quantum computation and logic, what's one question we should keep in mind?
I think the most important question to ask ourselves is, how does this new understanding of information and logic change how we see the world? How we think about knowledge and reality? Don't be afraid to question everything you thought you knew and embrace the strangeness of it all. Who knows what amazing discoveries await?
That's an exciting challenge. And for everyone listening, I encourage you to check out Quantum Computation and Logic yourself and dive into this fascinating world. Until next time, keep asking questions, keep exploring, and never stop being curious.